I'm going to go over the 2024 AP Physics 1 FRQs now that they've been released. I will leave I did a PDF with all the solutions. You can check that if you want, if you don't want to watch this whole video. I'm going to go over every question. Probably not going to explain it too much because it's a lot. It's a hour 30 exam. But yeah, keep in mind that even if you don't get the right answer, that doesn't mean you got no points, right? Because you could still get a lot of points just for showing your work. And I think sometimes they don't even give you a point if you get the right answer. They're just looking for did you do this step, did you do this step, all that kind of stuff. So don't worry if you didn't get exactly what I wrote. I might be wrong. I might get a bad score on this. So just keep that all with a grain of salt. I'm gonna start off with the first FRQ. So we had this loop-to-loop energy thing where there's a block of mass m and it starts here at rest and then it goes through this whole thing, and we want to figure out we want to do an energy graph thing. So the energy at point A, so this was for point A, and they had point A, point B, right? Point B was at top of the first loop, and what they were saying is hey, what's the energy LOL chart gonna look like? So they did it with bars, but this had a height of 6, no kinetic energy. So initially the height is 6r, and then afterwards the height is gonna be 2r, right? At this point, because it's one radius and then two radii off the ground. So you want to have two little thingies. I don't know what you call them, two bars up, right? A height of 2. And then obviously energy is conserved because there's no friction. So this has to add up to 6. So we're gonna do 4 for kinetic energy. The next question literally asks, hey, what's the speed at point B? You would have to apply conservation of energy. You'd have to say, hey, the energy initial equals energy final. That's a free point right there if you wrote that. And it was in the instructions too, so I really hope you wrote that. Energy initial, so UG at point A is going to equal to UG at point B plus the kinetic energy at point B. So if you substitute all your equations, mg, the height, so mgh, right? The height is going to be 6r. And same thing, mgh at point B, the height is going to be 2r plus 1/2 mv squared, and we're obviously solving for v. M's all cancel out, which is pretty nice. And then we just have to take 6rg minus 2rg, oh, that's just 4rg, is going to equal 1/2 v squared. 8rg is going to equal v squared. And then we're just going to take the square root. 8rg is going to equal v. So there you go. That is going to be the derived equation. You could do 2 times root 2rg. Whatever's algebraically the same as this would be fine, I think. And now obviously you're getting points did you do energy initial? Did you do all these steps correctly? So don't worry if you didn't get exactly root 8rg. Let's go on to the FBD, which was actually, I think, the last part of this. Oh, there's another sort of explanation, I guess. So we need to figure out, we need to do an FED at point C, all right? So I'll keep this up. At point C, we know that there's going to be the FN down and then the FG up. So really, I'm pretty sure if you just drew an FN down and then an FG down, that was probably it. You probably just could have earned all the points. Now, the question becomes, which is bigger, FN or FG? Now, I don't know if you had to do this, because it actually is kind of a lengthy-ish process. They gave you scratch work on the next page if you... Actually, am I allowed to talk? I don't know. Hopefully that was fine. So, FN and FG, right, you would have to say, okay, well, FN plus FG is the centripetal force. So that's going to equal mv squared over r. Well, what's the speed at point C? Well, you got to use conservation of energy. Similar here, right? I'm actually just going to branch off here. We had G6R. Now instead of 2R, it's going to be 4R. So G6R minus G2R, you should have gotten, and I'm literally just doing the same step, right? Instead of right here, 4RG equals 1/2 mv squared, it'd be 2RG. When you do the math, this is going to equal 1/2 v squared. So 4RG is going to equal v squared. You could like square root it, but look, there's a v squared right here. I can just take 4rg and put it there. So Fn plus 4 Fg, I'll say mg, is going to equal m 4rg. And then the r drops out there. So really you get Fn plus mg is going to equal 4mg based off the speed. So if this is mg and this is 4mg, this would have to be 3mg. This would be 3 times bigger than mg. So Fn would, in the most correct sense, be bigger. Did you have to do that? Probably not. I'm going to see. Let's see. There's nothing in here that says anything about relative sizes. And usually, on most of those FBD problems, they'll say draw it with the relative sizes. So I don't think that you actually have to do this. But if you did, shout outs to you. The next question, once again, it's all really about energy here. It looks like a circular motion problem, and it kind of is to a degree, but it's really energy. The next question says, hey, the minimum height that the block could kind of pass through point C is 4r. And we have to kind of, I just briefly explain why this would be incorrect. Well, the way I would kind of say that this is incorrect is say that, hey, if the height here was 4r, energy is still conserved, right, because there's no outside forces. So all the UG here would have to equal, well, all the UG here, because the energy at this point is UG, would have to equal the E final, which is going to be UG plus K. But this UG is going to be mg 6r, right, because the height is 4r. And then the UG here is also going to equal mg 4r. So if E initial equals E final and the UG are the same at both points, the K would have to be 0. It wouldn't be moving. It would literally like go up and then it would just fall. So because of conservation of energy, if the minimum height is 4r, it's not going to be moving at that point. And that was kind of the idea. Obviously, as I briefly explained, so you probably didn't have to be perfect on the explanation, but if you talked about conservation of energy, you talked about all that good stuff, you should have been fine. So let's go on to the experimental design. So if you have Mr. Fitz as your teacher, you're probably really happy with this experimental design because we did this in class. This was like one of the experiments we did, and so hopefully you kind of remember kind of the procedure. But basically, the whole question was asking that we have this sort of spring system going on. We have this vertical spring, and then we want to figure out what is the spring constant given a bunch of masses or cylinders or whatever. And I'll verbally explain the sort of experiment, but the kind of thing that makes this kind of unique from other experimental designs is we were only given the cylinders, a stopwatch, and a digital scale. You kind of had nothing else. So some of the things we could have done to measure this. Well, I guess I should explain part B, which is saying indicate the quantities, right? What would you have to graph on the vertical axis and the horizontal axis to get the K? Well, what I would have said is if we're only given time with the stopwatch and mass, well, if you think about simple harmonic motion, the vertical axis would have to be t squared, and then the horizontal axis would have to be mass, right? Because if you do t squared, and this is going to kind of be to briefly explain how you would use it kind of thing, but t squared versus m, the slope is going to be 4 pi squared over k. And you can write the equation, right, period equals 2 pi square root m over k. You could see that the slope would in fact be 4 pi squared over k. And then, yeah, we could just find out what the slope is and set it equal to that. So now I know for my experiment, I just got to measure the period of oscillation and the mass. So here's a potential experiment you could have said. All right, I'll just kind of read mine out loud because I kind of wrote it here. So procedure 1, weigh the mass of the cylinder as m with a digital scale and attach cylinder to the spring. So boom, bada bing. So I didn't include this here. I might have forgotten this in my explanation, right? You would let it fall and then kind of go to rest there. Pull the cylinder down such that the spring stretches, and then you're gonna measure. And I probably said release. I didn't say that here. Sorry. So release Measure the period of oscillation as t by using a stopwatch to measure the time it takes for the cylinder to go up and then back down to its original pull down position. Repeat steps 2 and 3 for multiple periods to find the average period. If the reason, I don't know why I'm stuttering so much, if the reason I included that was because in the thing it says, include any steps necessary to reduce external uncertainty. That's kind of the thing you could say. It's like, hey, find the average so that, you're not like going based off just one period. And then the final step I said is repeat steps 1 through 4 with different cylinders of varying mass, right? And that's going to what obviously you're going to graph. Mass effect on period. Alright, so that was kind of the experimental design. Hopefully not too bad, because we did this in class, which is actually really lucky for Mr. Fitz's class, and I think other classes as well. So we're going to go on to the next part, and okay, we had a bunch of these graphs. I'm not going to draw it because I want to save time, so I'm just going to show you on my iPad. These are the graphs we had. And you can also check the official, thing to figure out what the graphs look like. And yeah, we just kind of had to do some math stuff. So part C, using the data and the velocity versus time graph, calculate the change in kinetic energy. So what I would do, well, I'm just going to go to my iPad, I don't really feel like drawing this out, is I would say, well, the speed at 0.5 is 0.3, and then the speed at t equals 2 is 0. And then you would kind of find those velocities and make an energy sort of equation and solve for k. And I got k is equal to negative 0.0125 joules. So, awesome. Fuel's actually really small, so hopefully I didn't mess that up. And then, using the data and the force and time graph, estimate the change in momentum from the car. So, the force versus time graph, right, the area bound by the curve is the impulse, which is our change in momentum. So take a look. From 0.5 to 2.5, right, the total area is 0 because this area cancels out with this area. So if the total area is 0, the change in momentum is going to be 0. Okay. Do the data from the velocity and time graph confirm our estimation? It does, because at t equals 0.5, right? I'm just going to show you on my iPad. I'm sorry if this is kind of blurry. You can always check my key as well. From 0.5, it's 0.3. And then at 2.5 seconds, the velocity is the same. It's 0.3. So at both those instances, the velocities are the same. So the momentum of each thing are the same. So if the momentum is the same at those 2 points, for those 2 points, the change in momentum is 0. Obviously, it doesn't, it's not saying that the change in momentum is entirely 0. It's just saying from that time to that time, it slows down and then speeds up back to its original momentum. That's kind of the idea. And you didn't have to really explain that last part. That's just conceptually just to kind of get it. Okay, let's go on to the QQT. Okay, so we had a beam. I'll draw this one. We had a beam, and then we had, it's a classic, honestly. It's a torque classic. I was hearing some people today, and they're saying like, hey, I didn't use torque for this problem. That's kind of a problem because this is a torque problem, and hopefully you recognize that you were gonna have to do something with torque in this question. So we were given this beam, and then there's a wire attached to the very end, and we had to draw an FBD for the beam. I really hope this was pretty straightforward. The one thing that might have been a little, maybe people have gotten wrong or whatever, is we have to draw and label the forces, not the components exerted on the beam. So let's just start with the easy ones, right? We have FG and then we have FT. Hopefully you thought this through for a second and we're like, okay, no components. I can't do my usual force hinge Y, and then I can't do my usual force hinge X, right? We can always combine those two components to get the total force hinge as so. Be a little bit careful about that because it did kind of explicitly state no components. So, this is what the FBD would look like. Kind of what we've been doing all year long in terms of torque. because right, this torque and everything has to be in static equilibrium, all that good stuff. So the QQT part of this is saying, hey, when we change the angle, let's say we change the angle so that if this was our old one, let's make it dotted. If this is our old one, the new one is going to have a lower angle. What's going to happen to the force exerted by the tension? So, what you would probably want to say is, oh, I forgot, I should probably, in the future, have to actually do cross instead of check mark, because I think that's what you have to do. Whatever. Briefly justify your answer. Well, in both cases, the torque net is 0 in order to have static equilibrium. So when your angle decreases, the perpendicular component, there's kind of two ways to explain this. The perpendicular component of the force decreases because there's less angle, or the perpendicular component of the distance decreases. That's what we call our lever arm. So whatever way you explain it should be fine. The key idea is that in order to produce the same torque, because remember, about this center of axis of rotation, the torque by Ft has to equal the torque by Fg. Changing the angle didn't change the torque by Fg. It's still Fg times this distance, right? Same torque. So when we change the angle, the perpendicular, the lever arm, I like saying lever arm, makes more sense to me. The perpendicular distance, right, whatever's perpendicular with each other, that decreased. For the torques to be the same and to counteract each other, you would need a larger force. So I think the main key idea that we're looking here is, did you recognize that the torque had to be 0, the net torque, so therefore, if this decreases, that increases, kind of thing. Hopefully you didn't try using too many equations. You can reference them, I think. It's just you can't explain it just with equations. Okay, the derivation. Oh boy. After hearing what people did today, and definitely not at the exam when it ended, when I heard them today, a lot of people try to use forces, and that's kind of disappointing because it said starting with Newton's second law in rotational form. So hopefully you did, as your first step, tau is equal to I alpha. But we have to try to derive an equation for force tension. So alpha is 0 because nothing's rotating. So the torque net, this whole thing is going to be 0. So the torque by Ft minus the torque by Fg. Remember, they're opposite directions because one is clockwise, the other is counterclockwise. You don't have to really, as long as they're opposite, you're fine. 0 equals 0. So Ft times lever arm 1 is going to equal Fg times lever arm 2. And then we can start substituting angles in there. Ft R1 times, and then instead of R, we could just say L, right? Because that's the length, the distance. So FTL sine theta is going to equal mg 1/2 L, because it's at half the distance. It's at the center of mass. So hopefully that FBD kind of guided you there. FTL sine theta is going to equal mg 1/2 L. The L's cancel out, and then we're going to get FT sine theta is going to equal 1/2 mg. Just kind of, actually, just looking at this is pretty interesting to see that, hey, the force tension you need is like, it's going to be like 1/2 of Fg, right, in order to balance out the forces. So that's kind of interesting how, torque and, all your simple machines. But anyways, that's besides the point. You're solving for Ft, so we're going to divide everything by sine theta. And then algebraically, your answer should be force tension equals mg over 2 sine theta, right? Because that 1/2 goes to the denominator. All that algebra fun stuff. If you get something like this, you should be fine. The main idea to help you in the next part is that sine theta is in the denominator. So now, how does that equation? It's a very classic QQT, right? You're deriving an equation, relating it back to the scenario. How does this support our answer that we said? Well, we said that the tension should increase when the angle between them decreases. So in this case, our equation shows that force tension, it's not proportional to the inverse of theta. It's inverse proportion, or force tension is not inversely proportional to theta. It's inversely proportional to sine theta. And that's something you got to just kind of keep in mind, right? Because ft is inversely proportional to like the inverse of cosine theta, right? Things to be different. So remember that sine, not just theta, but sine theta, right? So as sine theta decreases, force tension should increases because this whole fraction gets bigger when sine theta increases. And when theta decreases, right, when the actual angle decreases, then sine theta decreases. So what does that mean? Well, if theta decreases, then sine theta decreases, right? Because if you think about unit circle, if theta decreases, force tension must increase. If this angle decreases, force tension must increase, supporting our original claim. Okay, so next up is angular speed versus time. So, angular speed versus time, omega versus time, really. This is one that I can see a lot of people messing up. So, what we kind of instinctively want to do is say, well, when this tension decreases, we have to draw the omega versus time graph. It's going to start rotating. So initially it's 0, and then at the end it's going to have some sort of angular speed, right? We could just draw a linear line. But what does that linear line mean? Well, that means, well, if the slope, right, for omega versus time is alpha, it's alpha, that means there's a constant angular acceleration. Now, what does a constant angular acceleration mean? Well, a constant angular acceleration means a constant net torque, because alpha is equal to tau over I, right? Net torque over rotational inertia. Constant alpha means constant net torque. What's the net torque when we decrease a rate, get rid of ft? Kind of depends on your axis of rotation. For simplicity, let's just say the axis of rotation is the hinge. Well, the torque by Fg is going to equal Fg, I'm not going to say L over 2, just FGR, right, the distance, sine theta. That's the important part, right? Well, we've been talking about sine theta here, it still applies here, because as this bar sort of falls, you can see Fg still points down. There's an angle in between them, right? There's this angle, and you can imagine, yeah, when it's completely vertical, the Fg is completely through the axis of rotation. There's no angle. It's producing no torque. As it falls, the torque decreases because sine theta decreases, because theta decreases. So everything, the torque decreases, your angular acceleration will decrease. So what does that look like? Well, it'll look like angular acceleration is our slope. Our slope should decrease, right? It's gonna kind of slow down. So this is not like an easy, like memorized kind of graph. You kind of have to think it through. So yeah, that was the entire QQT. Okay, let's talk about the paragraph length response. In my opinion, this was the hardest question. This was kind of the hardest one for me. It wasn't like you kind of had to think it through, and I think I could have gotten this wrong. So please take it with a grain of salt. But really, the first part of the paragraph length response was that justification, right? If you had a pendulum on two planets, right, and they start from the same angle and they start from the same, whatever, everything's the same, right? Same mass. But on Earth, we're on Earth, and then on this planet, the planet has a greater radius. What's going to happen to the work done by gravity as the pendulum bob swings to the middle? So here's kind of the justification. I don't know, maybe you hopefully explained more than this. I did, but this is kind of what I said. Greater radius means less g, because g is equal to gm, just one m, and that's the mass of the planet, over r squared. And so what I'm saying is greater radius means less fg, so less fg means less g. If you have a greater radius and less g, well, the work done by that planet is naturally going to be less, because work is equal to m, g, h, and height is the same, m is the same, and gravity is less, so the work done is going to be less. Hopefully you kind of explained it more than that. They're probably looking for a few things, but this justification is really going to be worth like 2 points at max. So there's not much you could have said, to be honest. So, yeah, that's kind of it, to be honest. Let's just go on to the paragraph length response. So, for this paragraph length response, you basically had a new pendulum, and it's made from the same sphere, but the string is a little bit elastic, so it can stretch and stuff, and it stretches, it like stretches. It can like stretch or compress based off the tension, so the length can change. That's kind of the key idea, depending on force tension. Okay, so the Earth, this sphere is displaced theta, and then we have that on Earth, right? It's the same stretchy pendulum. It's gonna have a period TE. On planet Y, same radius this time, but greater mass. Hopefully you read carefully and noted that. It's gonna oscillate with the period TY. The parallax response is, how could TY? How could it be larger than the period on Earth, but how could it also be smaller than the period on Earth? So here's kind of what I said. I'm going to talk about each of the 5 points. Not going to really write it down, but I'm just going to talk about what points I made. So here's my entire thing I wrote. Planet Y has more mass because planet Y, it's given, has more mass, same radius. So Fg on this planet is greater because Fg equals gm1 m2 over r squared. So if Fg is greater, the gravitational field strength is going to be greater. And specifically Fg on the bottom, right? So greater Fg compared to Earth, so greater gravitational field strength compared to Earth. So both pendulums start at the same height from the lowest point on both planets. The work done by the force gravity of I'd say that again. The work done by planet Y, the greater mass planet, is going to be greater because work is equal to 4mgh. So bigger Fg, same height, that's going to be greater force gravity, or greater work done compared to Earth. You might be saying, why are you talking about work? Where did you even get that idea? That's because that was the first justification we had to do. The thing about these paragraph length response is that the first kind of question kind of helps you with the next one. They kind of make you think about this stuff. So that's why I included work to be safe. If you talk about UG, that should be fine as well, as long as you made sure you said like pendulum, Earth system, all that good stuff. So the work done, and I think if you also talked about forces, that should be fine as well. I just did an energy response. So the work done by Fg is greater on planet Y. So the pendulum is going to be moving faster at the bottom, and I drew a picture of this bottom ramp, this bottom moment, I should say, lowest point, because it's going to have more kinetic energy. Sorry for the voice crack. More kinetic energy because more, more work is being done on it. If it's moving faster with the larger V, the Ft would have to be larger because in a pendulum, it's moving in a circle, and this is the part I'm kind of iffy about. It's moving in a circle. So if you think about, mv squared over r equals the centripetal net force, if it's moving faster, it's going to need a bigger centripetal force to get it moving up again, right? Like, obviously the forces can't be equal. If the forces are equal here, Fg equals Ft, then it's just going to move in a straight line, right? Like it's, no net force. To move in a circle, you need a centripetal inward net force. F tension is the centripetal net force, not the net force, but it's like the inward seeking force, right? Because Ft has to be greater than Fg. So if it's moving faster, faster V means faster, bigger tension, right? In order to move faster. So if it has a greater tension, obviously just based off what the problem said, the length of the pendulum could change because of that band, or the elastic string. Okay, so this is kind of where you have to talk about now the period of a pendulum. So the length could change now. We don't really know how it's going to change. It could like contract and shorten. So what I said is, hey, if the length, let's say the length increases, if the length increases way more, because obviously G increases as well, if length increases more than how much G increases, then the period will be longer, right? Because then length is going to be much bigger than G, right? Bigger period. If, let's say the length doesn't increase that much, or it even shrinks, then obviously G is going to be bigger, right? Length's going to be smaller. You can have a shorter period. That was kind of my whole explanation. So, I don't think this is straightforward. I could have gotten it wrong. I don't really know what that's kind of thing about the paragraph length responses. They typically have like a list of things that you want to say. I have no idea what that list is. Maybe I wasn't supposed to use energy. Maybe I was supposed to do forces. Maybe both ways work. So this is just my explanation. Just keep that in mind. I think maybe the main talking points are just talking about the force tension changes, how that affects the length, and all that good stuff. So to end off, let's just go over the last FRQ. We had an elastic collision on this one. So all the times I said, or your teacher said, don't use energy in a collision, well, you literally did have to use energy in this collision because it was elastic and we were given, right? We had a block. I might have to go soon, so I'm going to just hurry this up because I can hear my mom yelling at me. We have a block, right, and it's going to collide with this other block at rest. And we were given 2 kilograms, right, 6 kilograms. We're given the change in energy is 9 joules. So the change in energy of block 2 is 9 joules. So we just have to determine the speed of the block immediately after the collision. And I think this problem isn't that bad, right? Because you just did change in kinetic energy equals K final minus K initial. K initial is 0 because it's not moving. So then you just do 9 joules equals 1/2 mv squared. Pretty straightforward. And I'll show you my work. You should have gotten 3 meters per second. I'm just going to show you my work right here so you can, pause. You can take a look at that. V final is 3 meters per second. It said determine. Determine the speed. You could have gotten all the points by just saying 3 meters per second. You didn't have to show any work. So yeah. Showing works help though, because in case you don't get it right, you could still get partial credit, but you don't need to. Let's talk about the graph. So for the graph, position versus time graph, you have to draw and label the, at t equals 1, that's when they collide, right? Okay, yeah. You have to graph the velocity. Yeah, coming, Mom, give me 1 second. We had to graph the graph. So I'll just show you mine, I guess. I'll kind of talk about, because the main thing is the slope, right? I know that looks confusing, but really you just have to get the slope right for each block. Because slope is velocity. After the collision, velocity changes. So for the center of mass, you should have had the same exact slope, right? It should have been the same exact slope the entire 2 seconds. Because momentum is conserved, so the center of mass will continue moving at that same speed. For block B, well, we solved for 3 meters per second as the final speed. Might as well just use that as a slope, right? It's going to be a slope of 3 meters per second. For block A, you had to actually solve for its velocity to get the slope. You had to use you could have done conservation of energy. This is the one time you could have done conservation of energy in a collision. But you could have just done conservation of momentum. It's easier, to be honest, with all the, no squaring and whatever. We just did P initial equals P final. It's MV, so 6 kilograms times V initial. You were given the block A graph, and the slope before 1 second was 2 meters per second. And I'll show you what I mean. I'm talking about, this part right here, right? You could have found the slope 2 over 1, 2 meters per second. So, boom, bada bing, 2 meters per second is going to equal, well, MAVA plus MBVB. So, 6 kilograms VA plus 2 kilograms, 3 meters per second. So, this is going to be 12. This is going to be 6. So, if you subtract, right, you get 6 on this side. Divide by 6, VA should be equal to 1 meter per second. So your thing should have had a slope of 1 meter per second. Everything should have been just still increasing, like everything still moves, right? Everything still goes up, but yeah, there you go. And now for this final question. I know we got to the end of the exam. We just had one pretty simple question. What would happen if instead of colliding elastically, they stuck together? What would happen to the velocity of the center of mass? Well, in both cases, that was my brother, sorry about that. In both cases, the initial momentum is still the same, right? Because it's still the same block moving with the same speed. Initial momentum is the same. So in both cases, the momentum is still conserved. That's the key thing. Both cases, momentum is still conserved because there's no outside forces. That means the center of mass would be moving at the same speed afterwards. So it would be having the same slope afterwards because, right, P system equals mass system times velocity of the center of mass. Using that P equals mv equation, you can pretty figure out, well, if this is the same after and before the collision, velocity must be the same. So same center of mass, same line you should have drawn. That was the entire FRQ. So good job on this. You should be very proud of yourself. This was, yeah, I mean, it wasn't easy, right? Especially the paragraph length response. This wasn't like a simple exam. So yeah, hopefully you got some of the same stuff as me, because then that means I did a good job. But yeah, hopefully that was fine for you. Let me know if you have other questions. You can just text me or something. All right, bye. Thank you.